So I want to demonstrate sort of a trick called logarithmic differentiation. This is a way of using both implicit differentiation and what we know about the log function to make some derivatives easier to find. Now, if you look at this function, this is y equals x squared plus 1 times the square root of x plus 3 over x minus 1. This would be a complete mess to evaluate if we had to do it using the various rules that we know. If you look at what we have, we've got x plus 3 wrapped inside a square root sign. So that's a chain rule problem. We also have that derivative, that function is multiplied by x squared plus 1, so there's a product rule, and the whole thing is divided by x minus 1, so there's a quotient rule. This would be very, very messy to evaluate directly using the rules that we know. So there's a way that you can use logarithms to do this, and it's called logarithmic differentiation. So I'll show you what we do. What we do is, let me first of all just get a nice clean copy of this function. Let's paste. Let's write it in purple. There we go. So if y equals this function, what I can do is before I even do any differentiation at all, I can take the natural log of both sides. Now why would I do that? Basically because it's going to be easier to find the derivative of the log of the log of the right side than it is to find the derivative of the right side itself. So this is just an application of the algebraic principle that anything I do to the left I can do to the right. So I'm going to take ln of y is equal to ln of x squared plus 1 square root of x plus 3 over x minus 1. That means, using a little algebra, using just the law of logarithms, that's going to mean that the right side is ln of x squared plus 1 plus ln of the square root of x plus 3 minus ln of x minus 1. That's just using what we know about logarithms, how we know that ln of AB over C is equal to ln A plus ln B minus ln C. That's just rules that we already know. So I just want to show you one more thing we can do. Since ln of x square root of x plus 3 is actually equal to ln of x plus 3 to the 1/2, by another rule of logarithms that says ln of A to the B is equal to B times ln of A, I can actually just move this 1/2 over here. Now what I have is that ln y is equal to this log plus this log minus this log. This is going to be a fairly easy thing to take the derivative of. So let's take the derivative of both sides. Using what we learned about logarithmic differentiation, when I take the derivative of a function of y, I have to take its derivative, and then I take the derivative the normal way, but then I multiply it by the derivative of y. So this is going to be 1 over y times y prime, or actually I'll write it as dy over dx, since that's how we're being asked for it in the problem. And then here I have three functions of x. I can just take their derivatives. So that's going to be 1 over x squared plus 1, and by the chain rule I multiply by 2x, and then plus 1/2 times 1 over x plus 3, and then minus the derivative of, oh, I should say, by the chain rule, the derivative of x plus 3 is just going to be 1. That's why I didn't do anything there. So even though, yes, I'm using the chain rule step just comes out to 1, so I don't have to write it. And then here, this is going to be 1 over x minus 1, and then times the derivative of x minus 1. That's also 1, so I can just erase that. Okay, so now what I have is 1 over y times dy over dx is equal to this expression. So let's just multiply both sides of the equation by y, giving us dy over dx is equal to y times 1 over x squared plus 1, actually 2x over x squared plus 1, because I'm multiplying by that 2x, plus 1 over 2 x plus 3 minus 1 over x minus 1. And then finally, I really don't want to leave this y in. If I can write the entire expression in terms of just x, I want to do that. Since we were given in the problem that y is equal to this function of x, any place I see y, I can just replace it with that function of x. So this is going to be equal to x squared plus 1 square root of x plus 3 over x minus 1 times 2x over x squared plus 1 plus 1 over 2 x plus 3 minus 1 over x minus 1. And that is the derivative that we seek in this problem. And as you can see, although there was a lot of calculation, this was certainly much easier than trying to unpack this original expression using the chain rule, the product rule, and the quotient rule all at once. Another situation in which logarithmic differentiation is useful is when we have an exponent that includes a variable. Uh, First, let me show you the mistake a lot of people make. A lot of people look at this and say, let's see, y equals x to the 2 sine x. Surely I can find the derivative of that. And they go, y prime is equal to 2 sine x to the 2 sine x minus 1. This is this is very wrong. It's actually so wrong that I'm going to write an extremely bold wrong with 3 exclamation points. You don't do it that way. The power rule, the rule you're thinking of, like x squared, the derivative of x squared is equal to 2x, where you can just subtract 1 from the exponent and bring the original exponent down as a factor, that only works when the exponent is a constant. If the exponent has any sort of function or variable in it, this rule does not work. So you have to use different means. So let's try again using logarithmic differentiation. If I write y equals x to the 2 sine x, let's take the log of both sides. So ln of y is equal to ln of x to the 2 sine x. So now we can use a law of logarithms to simplify the right side. So let's write ln y is equal to 2 sine x times ln x. That's just, again, I'm just bringing down this exponent as a factor, just using one of the laws of logarithms that we already covered in one of the earlier examples. So now I'm ready to take the derivative of both sides of this equation. So on the left side, I have 1 over y. The derivative of ln y is 1 over y times the derivative of y by the chain rule, which is y prime. I said it's by the chain rule. We covered it in implicit differentiation. Why implicit differentiation really is just the chain rule. If you don't get it, then just remember the rule that when the variable is y, just take the derivative normally and then multiply by y prime. So, okay, so anyway, we have that's the left side. On the right side, we clearly have a product rule problem. So this is going to be 2 sine x times the derivative of ln x, which is 1 over x, plus 2 cosine x times ln x. Okay, so now what we want to do is multiply both sides of the equation by y. That gives us y prime is equal to y times 2 sine x over x, and then plus 2 cosine x ln x. And then finally, since we know what y is, we can simply replace y with its original definition in terms of x, and that gives us y prime is equal to x to the 2 sine x times 2 sine x over x plus 2 cosine x ln x. And that's the derivative of that function.